All right, we are going to skip over section 14.4. I will provide you a handout about this section in Canvas. It covers moments of inertia and some other applications of the double integrals. But we are going to move into 14.5, which is surface area. Which is also an application of the double integrals. All right, so let me give you the formula. The area of the surface S given by f of x, y, z f of x, y equals z over some region R is given by surface area equals double integral over R d capital S, where d capital S is the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA. Okay, so this is our formula for surface area under a curve over region R. I wanted to point out a couple things about this formula. So notice we use this capital S. If you recall, when we used a little s, ds was giving us arc length, right? And this formula looks really reminiscent of the formula we used in arc length. And in fact, remember in arc length, we had a function of only one variable. And so we just had this first term, right? So we had the derivative squared inside this square root. Okay, so this should look really similar to what we did with arc length, except now we've taken it a dimension up. Okay, that's what we've been doing all semester with Calc 3. We're moving into multiple dimensions. All right, so let's try an example of this. Find the surface area of the part of the plane with the equation 3x plus 2y plus z equals 6 that lies in the first octant. Okay, so we've done planes for a while now. You should first start by giving a sketch, and remember when you're sketching the plane in the first octant, really all we need to find is the points of intersection on each of the axes. Okay, so if I let x and y both equal 0, then z is 6. So we're up here at 6. When y and z are both 0, I have 3x equals 6, so x is at 2. And when x and z are both 0, we have 2y equals 6, so y is at 3. Okay, so here's my plane. And I want the surface area there of that plane in the first octant. And this is exactly where that plane is in the first octant. What's my region of integration R? Well, it's this region down here below in the xy plane. So down here is R. Let's sketch that. So I crossed at 3 on the y-axis and at 2 on the x-axis. So here's my region of integration. Now I can take this as a vertically simple or as a horizontally simple region. I think I'm going to go ahead and go vertically simple. So this is delta x. And so first I want to think about bounds on y. as I take slices in here going vertically. Y ranges from 0 up to the line. This is the line that is the equation of the plane when z is when z is 0. So this is 3x plus 2y equals 6. And rearranging gives me y equals, let's see, negative 3/2 x plus 3 is the equation of the line, and we're going from 0 to that. Let me scooch this over so it's not so crowded. Oops. All right, what about my bounds on x? Well, again, if I think about as I take these slices, what are the x values? The x is going this way, and I'm going from 0 to 2 as I take vertical slices here. So my bounds on x are 0 to 2. All right, so now I'm ready, almost ready, to set up my integral. So I want to plug into this formula. I need the partials with respect to x and with respect to y, and I need my equation in the form z equals f of xy. So let's do all of that. So first of all, I want z equals 6 minus 3x minus 2y. And now, what is fx? This is my f of xy. So the partial with respect to x is just negative 3. Partial with respect to y is just negative 2. All right, so surface area is the double integral over r of the square root of 1 plus fx squared, so negative 3 squared, plus partial with respect to y squared, negative 2 squared, dA. Let's go ahead and fill in our bounds here. We want x to run from 0 to 2, y from 0 to negative 3/2 x plus 3, square root of, let's just do that. I have 9 plus 4 plus 1, so square root of 14 dy dx. All right, I'm going to go ahead and run through this integral with you quickly. So I get the integral from 0 to 2. When I integrate here, I get square root of 14y evaluated from 0 to negative 3/2 x plus 3, and I've still got my dx here. It's the integral from 0 to 2 of, well, I'm going to just take square root of 14 times negative 3/2 x plus 3 dx. What do we get here? I'm going to pull my square root of 14 out front. I get negative 3/2 times x squared over 2 plus 3x evaluated from 0 to 2. That's square root of 14 times negative 3/4 times 4 plus 3 times 2. The 4's cancel, so I have negative 3 plus 6. That's 3. So I get 3 square root of 14. So that's the surface area here, the purple that's been shaded. All right, I'm going to let you try a problem and then we'll do another example.